Hello? Okay. So let's start. Thanks everybody for making it to rainy Baltimore. And we'll start out with a few remarks from our interim deputy director, Mark Postman.
So good morning, everybody. And as Massimo said, I am Mark Postman. I am the interim deputy director here at Space Telescope, and in that role, it gives me a great pleasure to extend a warm welcome to everyone here, both those in person and those tuning in online. Today, we begin what promises to be a truly captivating conference that celebrates the first year of science with JWST. And what an extraordinary year it has been. JWST is not merely a novel telescope. It is a beacon of human achievement. It was realized through the collective efforts of over 20,000 people working at NASA, ESA, CSA, various aerospace companies and universities, and right here at STSCI. Together, they helped to conceive, design, build, and commission what is one of our most powerful telescopes, and certainly the most complex and capable space telescope to date. Thanks in particular to the 800 dedicated and talented people who work right here at STSCI for enabling use of this wonderful facility by the global astronomical community, which is our goal, of course. But that's not all. We have a lot more planned. Given forecasts indicating abundant onboard fuel, JWST may last up to 25 years, or perhaps even more if electronics hold up. The opportunity to be amongst the first people to use this remarkable facility that has already, in fact, expanded our view of the universe is a privilege I'm sure we all appreciate. But trying to keep pace with the results coming from JWST can be a daunting and challenging task. The sheer volume and diversity of discoveries are both exhilarating and challenging, and that's precisely the kind of challenge we love to embrace. It's one of the reasons, in fact, we've had this conference here today. Over the past year, JWST users, including many among us here today, have published findings that require us to rethink our paradigms for planet, star, and galaxy formation and evolution. And these revolutions include massive galaxies that appear to be in existence just a few 100 million years after the Big Bang, and now backed up with spectroscopic confirmation, placing them firmly at redshifts of 12 and 13. Further evidence for the Hubble tension, potentially paving the way for new physics required in our cosmological models. Detection of significant evolution in the black hole mass-stellar mass relationship. Unveiling the predominantly molecular composition of outflows in very young stars. The first detection of carbon dioxide in the atmosphere of an exoplanet. And the ability to potentially characterize a new class of potentially habitable ocean-covered sub-Neptune worlds, enabling remarkably deep surveys of icy bodies in the outer Kuiper Belt. And this is just a subset of the one-year science. Imagine what the next 10 years will bring. The impact of JWST on astronomy and astrophysics, however, is not measured just by the science produced, but also by the inspiration it provides to future scientists and engineers. And we will witness this directly at this conference, as many of the talks are being given by graduate students and postdocs. Moreover, JWST is set to leave an indelible mark on the world, just as HST has done. Hubble has become an icon of scientific and human achievement, and JWST's legacy will also be defined by how effectively we share the awe-inspiring wonders its instruments reveal with the public. Lastly, I want to extend my gratitude to the STSCI Events Planning Group and Sharita Hanna in particular, for their remarkable logistical prowess, and to Thomas Marufu, Gary Gilbert, and our AV team for their excellent support of this meeting. Finally, I also want to extend a thank you to the Scientific Organizing Committee for assembling such an exciting array of speakers spanning a wide range of astrophysics today. So let's get to it and begin this fascinating meeting. Thank you.
So let's start with the first speaker of the day after the introductory remark, the Senior Project Scientist for JWST, Jane Rigby.
Good morning, everyone. Thank you for being here. I realized on the drive up there was a bunch of stuff that wasn't in my talk, and I was having deep regrets, and Mark just hit all of the things that I left out. So thank you. I will echo all of that. Thank you for being here. There are folks in the room.
This is Jane Rigby.
Hello. I hope I'm not leaving the meeting, because I feel like that would be, okay, can you hear me all right online? So thank you for people who are here. Thank you for folks who are joining us online. Oh, power's off? Well, there you go. Now there's very good. Now there's a green light. I want to acknowledge that there's folks in the room and joining us online who have worked on this mission for decades, as well as folks who are new to the project and coming in at harvest time. And always it's the case in astronomy that we are picking olives from trees that we didn't plant and putting new gardens in the ground. So they asked me to talk a bit about how things are going. Short answer, great, but I'll give you some details on great, okay? First off, I wanted to remind you, as you're writing science papers, to please cite the instrumentation papers. There is a PASP special, I'm gonna deal with the AV here because it's stupid. You guys don't want to hear this for an hour and a half, right? Because it'll feel like that long. Better, okay. Thank you. So please cite the instrumentation papers. George Ricci, who's in the audience, was the editor of a PASP special issue describing the performance of the observatory and a summary of the whole enchilada, the mission, each instrument, how it was designed and built, how well it's performing. So this is a way of acknowledging those decades of contribution. So please do that, and if you scan the QR code, there's a nice landing page at PASP which has links to all the papers. Good. So when I say things are going great, here's some documentation of what great looks like. This is how the optical stability of the telescope has performed. Can we kill the echo? Sorry. This is how the optical stability has performed since we got out of commissioning and started science operations until last month. And what you're supposed to see here is, oh my gosh, the telescope is much more stable than requirements. And so on the y-axis here is the wavefront error in nanometers. And Susan asked when she was checking over my charts why there was this number 150 at the top. That's the requirement. So if we hit that number off the chart, we would still be as good as we promised. But in fact, we're hovering here in the 70s, and the telescope quietly moves along. And then at the cyan green lines are when we correct the telescope. So when the wavefront gets worse than our tolerance, we correct it and bring it back down. And we're monitoring it every 2 days, but it has been shockingly stable. You can see it was more unstable early on. Those are tilt events that we think are that are clearly becoming less common as we go on. And for the last several months, we have just been in this beautiful realm of stability, and you're seeing that in the data that we're all working with. There we go. The telescope is more sensitive than expected. This is all now documented. This is in the PASP special edition. But the point here is that yes, indeed, we're 2 orders of magnitude in sensitivity more sensitive than previous instruments, which is what we promised, and then a little bit. The one exception, of course, is MIRI MRS at the longest wavelengths where we have an anomaly. There is an anomaly. There have been multiple there are links here. There have been multiple JWST Observer news articles about this to make sure the community is informed. The short answer is here is that we are not yet sure what the root cause is, but we're seeing that the number of counts has gone down with time in the long wavelength channels. And so you can see that these are observations taken a year apart. You can see the count rate drop. Okay, so if you have questions about that, talk to the help desk after you've read what is on JDocs and what is in the news articles. The stray light numbers are better than expected. This is also already published in the PASP, but the point here is that we didn't have to get this scenario. The sky is darker than we expected for JWST, which really is a testament, this would have met requirements up here, where the y-axis here is how long do you have to stare, relative exposure time, as a function of how dark the sky appears to JWST. This is what would have met requirements up at 40% longer integration times to get the same sensitivity. What we got is a bit better than we expected, which still beats the pants out of requirements. Right, so this is really a testament to all the work of the engineers to build a telescope that has very minimal stray light and that isn't seeing its own reflections rather than the real sky. This is not a great slide on efficiency, but this is a slide on efficiency. In here, the yellow is time we're spending slewing. Red is dead time, so either waiting for a target to come into view or anomalies, or other times when we're not observing. And green is when we're observing. So this looks really great. That's an 83% efficiency, but y'all should be asking, hold on, what about all the overheads? And all the overheads are in this green thing. So when we're, say, turning a filter wheel or doing a small angle maneuver to dither, all of that is counted on green. So you should be unhappy with this and demand a better plot from me that shows what our actual time spent integrating on target is. And that's something more like 50%. I would say where we are right now is the telescope is working beautifully. There are some ways to eke out efficiency gains. There aren't obvious, easy ones where we would have done it, but there are places where we can get little efficiency gains here and there. You got to talk about micrometeoroids. We expected before launch, and it was in the budget, that the telescope would suffer degradation due to micrometeoroids, little tiny things hitting the mirror. And we have fantastic wavefront sensing, so we're extremely sensitive to these micrometeoroid events. To date, we've detected about 50 of them. The hit rate is consistent with the pre-launch predictions, about 2.6 per month. And what is not consistent with predictions, what is in fact really surprising, is that if you plot the cumulative effect on the wavefront of each of those, you get a histogram that has 50 of them with basically no damage after correction, and one of them with 9 nanometers of damage. And that is not a histogram that is not Gaussian. So that's something that we have spent a lot of time trying to figure out why that one hit back in May, which you can see here. It is a dinner plate size deformation of that segment that will be with us for the length of the mission. What was up with that event? We now know we haven't been hit like that again in more than a year. But we do know if we got 10 hits that big, that would take us to that 150 line at the top of that plot, right? That would take us to our end of life requirement. So that's why in cycle 2, we are reducing the amount of time that we're spending pointing in the direction of orbital motion, right? Where the Earth's motion around the sun is adding to the kinetic energy of these particles that we're hitting. So when we have a choice for sidereal targets, you can observe them when the telescope is moving toward the target, or you can do it when the telescope 6 months later is moving away from the target. We are preferring to look in our wake direction rather than in the direction we're going, right? In the direction of the rain. In cycle 2, we have, by doing that, reduced the amount of time we're spending pointing in a cone toward the direction of orbital motion from about 38% down to 20%. That does affect schedulability, that does affect efficiency, and so that's the big answer of what's going on. We're trying to preserve a long and healthy lifetime for this telescope. So we are minimizing the amount of time we're, not eliminating, but lowering the fraction of time we're spending pointing into the rain. And the total amount of damage so far from micrometeoroids, is not a big deal. Okay, calibration and pipeline. I'm sure there'll be more discussion of this. There is an upcoming calibration workshop to put on your radar for November, where we want folks to bring their ideas and their algorithms here and discuss those. But I would say personally that the pipeline and the calibrations are not where they need to be for all 17 instrument modes. And that's a lot of work, right? We have 17 instrument modes that need to be fully calibrated. And users, of course, want that. And when we selected the Cycle 1 science program, we didn't select science that didn't require good calibrations. We selected science that was compelling. And now we're having to get those calibrations to their ultimate state that is needed for some of these programs. So I don't want to minimize the amount of work involved in that. We have 17 instrument modes, 10 detectors on NIRCam alone. There are nonlinear issues. The telescope is so sensitive that you're transferring calibrations from very bright things to very faint science targets. And I just want to say that for me, this is a big issue in terms of maximizing the scientific capabilities of the observatory to really get these calibrations on the pipeline to where the community expects and what the science deserves. So I get to sit here for the rest of this conference and take lots of notes and say, ooh, a lot. So I'm very excited for the work that y'all are doing to learn more. I would say the hardest part of my new job right now is keeping up with the pace of scientific discovery because y'all are working so hard. So thank you. I'm not saying slack off, no. I'm excited for this conference to hear about the new results. And thank you so much for your work of doing the science and then explaining the science to your peers and to the public at large. So that's a summary of, and also please don't be a stranger. There are multiple ways to be in contact with us. There's a help desk. If you are encountering issues, please put a help desk ticket in. That's how we know there's an issue. Please send feedback when there are surveys, and there's a JWST users committee. Please send feedback to them. We are listening. We want to make sure that we are doing right by the science and meeting your expectations. So thank you so much, and I'll take any questions.
Thanks, Jane. Eric Smith, NASA headquarters. Just a quick question on the pipeline issue. Is it, I'll say, are the deficits you're seeing because there hasn't been enough data collected to calibrate it well, or is it just do we need to throw more bodies at it?
So the calibration, actually, so no, it's not a matter of not taking the Cycle 1 calibration data. That was, I know, it's Monday. Mondays are hard. The calibration plan was built in a Cycle 1 that executed actually a little earlier than scheduled. We have the data. There's a lot of work to build each one of the calibrations. Those are proceeding. I think some of the work has been communicating to the community where can you trust the data and when can you not in terms of the calibration. And my other sense is that for the pipeline, it's really, we have these very powerful pieces, and then there's parts where you need to attach 3 rubber bands to do a workaround. And someone has to tell you where those rubber bands go. And so it's a matter of documenting that, communicating that, and then improving the pipeline so it doesn't need the rubber bands, right? That the pieces are strong, but right now the connecting them to get a data product through the whole way is something that there are experts in the room who are really good at. But I want to make it the case so you don't have to be an expert, that it just works for the average user, which is, for me, in part, really seems like an equity issue. That an average not well connected to the teams or that built the instruments or that are at big universities can get world-class data out of the telescope. Because clearly the data is, you can look at the raw data, the data is clearly producing, the data is amazing. It's a matter of getting those calibrations to where we want them to be. And it's a young telescope, and we all have both impatience that we want to get to that precise calibrations now, and it's a young telescope with the data have a number of features. And we have 17 instrument modes. If we just didn't take so much spectroscopy, this would be easier.
Janice Lee, Space Telescope Science Institute. Hi, Jane.
Hi, Janice.
So I find the idea of robotic servicing missions to L2 so exciting. What can you say about that?
Robotic servicing missions to L2. So Mark already hit that we have 20 plus years of propellant. That's thanks to a perfect launch by Arianespace, a perfect injection into the second Lagrange point by our flight dynamics facilities, perfect propulsion thrusters. It's still cool to me you can fire thrusters you've never fired before, and they work to 1%. That's neat. And we had a great launch date. So because of that, we have propellant. That before launch was the limiting factor, right? We do not have onboard cryogen that is non-recyclable, right? So we're not like Herschel or Spitzer, we're gonna run out of cryogen. So we don't have a consumable problem right now. Technically, before launch, we had a consumable problem, right? We had gas in the tank for 10 years. Now we have more than 25 years of propellant. So the question is, what do we need servicing for? For this mission, I don't know that we need servicing. We have propellant, and the science instruments are packed into the middle, and you're never going to get at them the way you are for Hubble. So you tell me what we need it for.
Well, we have a problem with Miri MRS we could fix, maybe?
What?
I don't know. I'm not, yeah.
Yeah.
I mean,
So-
there are a whole bunch of reasons you would imagine.
The 30-second...
Adding new capabilities.
Sure. The 30-second fundamental difference between Hubble, which was serviceable, and JWST, which is largely not, is that Hubble was launched by a big pickup truck, the space shuttle, and so they had weight. They could spend a lot of weight. There's tons of mass, and so you pull each of the instruments for Hubble out on rails. They come out on rails with handholds, and it's easy to get at the instruments. For JWST, everything was about lightweighting it to get it out 1 million miles away. So JWST weighs half as much as Hubble, even though the collecting area is 7 times larger. As a result, everything about JWST is lightweighted, and the science instruments are packed into the middle of the science instrument package and are incredibly hard to get at. So I think that it's a different framework for JWST, is that, in fact, you could argue we serviced it on the ground. We swapped out the detectors for ones that did not have issues before launch so that they will work correctly up there. But I think that that's not the right paradigm, because it was built to be light, not to be serviceable.
Still have time. There are other questions. Ale and then Roger. Alessandra was faster. Sorry, Roger.
Oh, it's speed on the draw. More caffeine.
Actually, I want to make more of a comment, which is also JWST practically has a 50% efficiency, because you don't use all the 95 minutes of the orbit, only about 40. Like with the overhead. So getting to 85% efficiency, including the overheads, is pretty damn good in the first year of operation. So Hubble took a long time to get to the level of efficiency.
If I haven't already said so, I'm really pleased with how we're doing a year out. And yes, in terms of how well the observatory is working, I expected way more anomalies than we've had. Maybe I'm just a pessimist. It's been really smooth. I feel like we've really hit our groove on scheduling. It is still very artisanal in some ways. And we could get the guide star rate is working as well as Hubble. Maybe we could do better than Hubble. But yeah, we say here are the issues, but it's working remarkably well for a year into science.
Jane, first of all, Roger Windhorst, Arizona State. Thank you and the project and the instrument builders for building such a remarkable, long-lasting facility. Unbelievable. Thank you very much. My question was about the micrometeorites. Do you need to take any special measures during the known, couple of day-long streams from old comet trails?
So that's a great question. So there's a micrometeoroid working group that formed after we got that hit a year ago in May. And that includes experts from many different, it's a very multidisciplinary group. That includes the folks down at Marshall Space Flight Center who are the experts in the weather of micrometeoroids in the solar system. They have made for us beautiful forecasts of what to expect, including the additional risk from each of the known micrometeoroid comets, right, the trails of comets. And the end result is there's only 1 or 2 of those comet known,
Trails, yeah.
times when you go out and lie on your back and look at the meteoroids, right? Look for meteors. There's only 1 or 2 of those that we care about. For those, yeah, we can point away from them, but most of the risk is from these little, they're not associated with any comet, they're just out there. So they've given us really beautiful forecasting that has helped us to understand that. We are also hitting pieces of beryllium with simulated micrometeoroids. We've been doing that in the lab over the summer, which is exciting, just to better understand that translation between of how the mirror gets damaged. But I want to emphasize that we knew this was going to happen. It's really more an understanding of where in detail the vulnerabilities are, and in particular, if there's certain ways that the mirror that can be more likely to sustain damage.
Thank you.
There are no questions online, so I think we can thank. And move to the next speaker, the STSCI JWST project scientist, Macarena Garcia Marin, will tell us about science timeline and future plans.
Thank you, Massimo. How do I sound? Okay, great. Well, while the slides come up, I want to echo Mark and Jane. Welcome, everyone. It's really, for us, exciting to have you all here. I think we're going to listen to great science in many different topics, so thanks. Looking forward to this week. And thank you for everyone who is online as well. So Jane has really set up the first part of my talk perfectly, because we're going to talk about calibrations and pipeline and kind of the plan we have to improve all those things. And then we're going into cycle 3. This is a little outline. So data to purpose initiative, you'll learn what that is now. We're going to talk about the JSTAC, so you are all aware of what the JSTAC is and who are the contact people, etc. A little bit about the cycle 3 timeline, proposal resources, and then just a tiny bit about newsworthy results and how to actually have them published. So in recent months, STSCI has received direct and indirect feedback about, issues with the pipeline, the calibrations, and in general expressing that the data, going from your data to good quality, publishable results often takes a lot of effort and workarounds, etc. So there have been key concerns. For instance, the documentation is insufficient. There is not a clear information about what the plans are, when the calibrations are going to come out. The description of calibration, it's not sufficient. So essentially, it is not only about what the pipeline is doing, but it was also a lot about communication and also when things are going to come out and what can we expect, and also what is the quality of the current calibrations. Also MAST. In general, some people feel that MAST is difficult to use and things could be improved. So in response to all this, we have launched what we call the Data to Papers initiative, which essentially focuses on prioritized communication, software development, and calibration activities to help you all best to go from your data to actually having data that you can publish and confidently compare and use. And I'm just going to go very quickly through kind of the highlights of this project. So number one, because this is all about communication, first thing is to gather feedback from you, from all the science community. We're going to have a cycle 3 survey, user survey after the cycle call, so please fill it out. We have a cycle 2 user survey that has been very useful to, on reading and doing statistics, identifying what are the areas of improvement. And we read all your comments, so don't be shy. Just write them all. It's all good. The more, the merrier. We do have JWST Observer news items. If you're not subscribed, please, because we put there a lot of interesting news. And recently, we did have a piece in June to encourage everyone to use the JWST help desk. You don't have to use it only when there is a problem or only for some specific, say you have an issue with the pipeline. You can also use it to give suggestions and to provide feedback. And if there are enough of the same question, then they are converted into a little article at the help desk that is useful for everyone. So your input is actually very useful for the entire community. And finally, as I mentioned, we have the Improving JWST Data Products workshop in November. So this is not a training workshop for the pipeline. This is a workshop for having experts in the community, and I'm sure there are many of those in the room. So people who have taken the calibration pipeline and gone through the next steps. You're improving calibrations, you're improving software, you have new ideas, fresh ideas. So we want to hear about those. And the ideal scenario will be to identify algorithms and perhaps new code that we can then implement in the pipeline and improve it. So that's kind of the concept. Registration is open. By the way, throughout the slides, I put a lot of links. I will certainly share the slides so you have access, easy access to all this. So once we gather the feedback, the next step is to inform the user. So the first thing we've done is what we call the known issues with JWST products data page. So this is a JDocs page. And the concept is very simple. So there is a table per instrument mode. You have them all listed here. And that's just a little snippet of one of the examples of the table. So you have one column where there is a description, like really user-driven description of what the issue is. It could be, I don't know, there are too many bad pixels on my data. It can be anything. So you have a symptom, then you have a cause. So the root cause could be, in this case, for instance, aggressive outlier detection. In some cases, it could be under investigation. It really depends. Then we have a workaround. The workarounds could be, perhaps, don't run this step in the pipeline. Use this this notebook that we are providing, or maybe wait 2 weeks until Mass will reprocess everything. So depending on the case, there will be a different workaround. And then finally, the mitigation plan. That is, what is a solution? And in general, it could be, when can you expect to have a solution in the pipeline that will be run by default? So this is, I really encourage you all to go to this page. This should be in your bookmarks, so you can quickly go and see, oh, I see this issue on my data. Is it on the table? So that's kind of the first question. Do we even know about it? If we don't see it there, send a help desk ticket. Let us know, and then we can take it from there. Also, on the informing users, the teams are working currently on creating a single calibration uncertainty page. Again, by observing mode, where you will find what is the uncertainties of all the calibrations we have right now and where we can expect to be in a while from now. So that will be, I think, very useful. All of this will be shared by email, and probably we will also have an observer news item, so you are all aware of, We want to have like 2 single links that you can easily go to and check the status of the pipeline and the calibrations without a lot of effort. We're also having a new series of JWebinars. The first 3 in September. One is for MAST, another for the ETC, another for APT. So this is, for the most part, really proposal planning driven, because we're in the middle of a call for proposals. But the next JWebinars will be focused on pipeline and data analysis. And by the way, there is an upcoming new, I don't want to call it MAST because the name is still under development, but a search engine, if you will, for JWST. If you're familiar with the new HST MAST search, so there will be something similar, and a beta version will be used in this JWebinar. So if you're curious, register, join, you'll see it there. It really works very well. Finally, there is always calibrations and pipeline. It's an ongoing work. Following up on Eric's question to Jane, part of the challenge of the pipeline is that it has to run for all 17 modes, all types of data, brightness, and it has to run automatically. You don't have any sort of interactions. And that is part of, some science cases may suffer, like if you have something too bright, maybe your linearity is not as good, or if you have something too faint, maybe, I don't know, the snowballs are really having an impact. So it's really, it has to be very robust and it has to run independently, and that's part of why it is challenging, and we're working on it so much. So my little takeaway for this is a partnership between the mission, in this case STSCI, and you all, the community. So we really want to hear from you. We really want to hear what the status is, what the issues are. There are many ways to provide that feedback. You can fill in the user survey, you can send a help desk ticket, you can reach out to your JSTAG representative, you can even send emails. So just please communicate. I think that's the key message here. As I mentioned, there is a new JWST-specific search form that will be available very soon. And if applicable, consider applying to the workshop coming up in November. It's really all about, I'm sure in this room there are people who have done tricks in the pipeline and tweak things here and there. So that's what we want to hear. Do you have a new fresh algorithm to do, I don't know, a snowballs correction, just to say something? We want to hear about that. Okay. What is the JSTAC? So the JSTAC is a committee established by STSCI and NASA Goddard Flight Space Center, and it's a joint committee that is essentially providing advice coming from the community to the mission. And it's the mission as a whole. It's not only the pipeline, it is the pipeline, it is efficiency, it is micrometeors, it is anything that is relevant to the observatory and to the mission. So they provide that. The JSTAC members, they are your representatives. They are there to represent the scientific community, and they are really happy to take the feedback and bring it back to the institute. And they often write letters, provide recommendations. We meet, we're meeting soon, I would say maybe twice a year at this point, at least this year. And they always have feedback, and we work together to try and improve things. So please communicate with them. I put there the website from the JSTAC. Everything is public. The letters from the JSTAC, the presentations we give to them, all the discussions, it is there. And there's also a nice email. So if you click on that email, in the website you can directly email to the JSTAC chair with whatever issue or feedback you have. And this is the list. It's not, I mean, we're not going to go through all the list, but this is the list of JSTAC members. There are members on US, Europe, Canada. Just reach out if you have any issue and know that they are there. It is yet another venue for communicating with us. Let's move into cycle 3 because we are in the middle of a call for proposal. So this year is an exciting one because we have 2 deadlines for JWST, and really hoping that you all will apply again and get as many applications as possible. So the cycle 3 will start in July 2024, and it will end June 30th, 2025. But the deadline for the proposal is October 25, 2023. So it is coming up relatively soon. The peer review meetings will happen between January 29th and February 8th. And after resolutions, there will be a budget submission deadline for April 11th of 2024. The notifications of the outcome of the selection process will be about late February, early March, so around that timeline. One note, successful JWST proposals are eligible to apply for NASA high-end computer capabilities, so essentially supercomputing. So there is a possibility of applying for that should you need it or should your program need that. And that's a link for that. So the next slides are just some snippets of useful information. All of this is in JDocs. A lot more is in JDocs. I think often JDocs has so much information that it's hard to navigate. So we wanted to kind of consolidate a bit of the highlights in here. So to propose, you obviously need APT, you need the ETC, you don't need access to documentation. So APT, we are using a version 2023.5.1. There are a few new things. So there is a new joint observatory proposals with NRAO, so that is available for cycle 3. We do have a new geo archival proposal type, and that flag is on APT. We have added NIRCam wide field slit spectroscopy as a pure parallel, so another powerful mode to actually get more science return. We have interfaces for optional first short exposures with NIRIS, single object slit spectroscopy, SOS template, and finally the survey allocation now it is changed to match the method for the Hubble Space Telescope. In the ETC, you should use the version 3.0. There's a link there. In that page, in the page of the ETC, you will have a link to what is new in this version, and if you go there, you can see all the new things. A few highlights, talking about the MIRI-MRS, the ETC has now implemented the predicted MRS sensitivity for the end of cycle 3. So if you use that ETC, you're going to get a good value that will get you, the actual signal-to-noise ratio. It is actually a bit, on the conservative side because it's for the end of the cycle. There are updates to IFU strategies, and there are also some specific updates per instrument. So if you're curious, you can check all of that in the release notes. In JDocs, there are many pages that have been updated. So if you don't know it, JDocs has a breaking news page, and that page captures all the pages that have been updated and any other relevant new information that's available there. So please visit that. The call for proposals. This is the JDocs page, and that's the link up there. And I wanted to highlight two little things. There is a late breaking news on this page, and this is really useful. Anything changes, anything the ECT wants to communicate, like, I don't know, like changes in policies, anything relevant to the proposal that is last minute will be captured in there. And this is a where to get help. Please reach out if you need. There are not only documentation, but I think by default, as Jay was mentioning before, send help desk tickets. We love to have them. They're useful. They inform everyone. There is also a page that has a little proposal checklist, just to check all the bases, and you can go through it and see. It is a suggested workflow, but it covers everything you need to kind of do for submitting a proposal, including deadlines, documentation, etc. So what are the proposal types we have? I'm sure you're all familiar, but in general, we have small, medium, and large proposals. So a small is less or equal to 25 hours. A medium is between 25 or less or equal to 75. Large, more than 75 hours. This is total time, including overhead. So APT will give you the total time, and that's what will determine where your proposal, in which bucket it lands. The geo proposal categories in General Observer are, of course, small, medium, large, and then we also have long-term geo proposals. These are the proposals that they extend through 3 cycles in this case. So for this call, there will be cycle 3, 4, and 5. This is, you must provide a scientific justification. Say, for instance, schedulability is not a reason to have this, but if you have a variable source, that is a reason to have that. So that would be an example. The total time across the cycles determines which category, small, medium, or large, the proposal is. We have Treasury geo proposals. These are really designed to create lasting scientific value for the community, for all of us, essentially. And these are generally large data sets. They tend to solve multiple scientific questions at the same time. And also, the expectation is that the data products will go beyond what the pipeline offers. And that would be part of a Treasury program. We also have calibration proposals, and those are, we have calibration plans for each cycle, and we are getting calibration, as we all know, is an iterative process. It takes time, it takes compiling data, and we're focusing on the most important things. You may have an idea, or you may have noticed that, hey, this particular mode perhaps would need a little bit more calibration. That would be an opportunity to put a calibration proposal. And of course, all these have links to the lengthy explanations in JDocs about that. And we have a new category that is a combined geo-archival proposal. So a fraction can be an archival, up to 10%, and then the rest would be a normal geo proposal. This is in answer to needs raised by the community. Yeah, 2 minutes, thank you. Other proposal categories are, almost finished. Archival research, use archival data, survey programs that they are used to fill in the timeline or to cover, to use for times where we have lower bandwidth, essentially, and joint survey programs with other facilities. Finally, proposal resources. So please go to that link. There are many of them, and they're very useful, so it's worth checking that out. Finally, what do you know if you think you have a newsworthy result to be in the media? So essentially, please reach out to the STSCI's Office of Public Outreach. If you are a European group or European scientist, then that will be sent to ESA for consideration. I would like to highlight Christine Pulliam, who may be in the audience. Oh, there she is. So that's Christine. If you have a newsworthy item, talk to her. We have 2 types of new items. In general, they require a peer-reviewed journal, but sometimes if they have been presented at the AAS or if they have just an image release, they are accepted. And it all comes with significant discussion. It has to be suitable for the public, etc. But this is the form you can use to submit it. Please come early. Don't wait until last minute. 4 to 6 weeks is an ideal time. Reach out to Christine if you have newsworthy. And I really look forward to see more news, the results from this week. And that's my last slide. So let me know if there's any question.
Thank you.
questions online, so let's see if there are any in the room.
It's very clear. Yes.
Macarena, I think the geo-archival proposal category, the new one, is a very good idea. Does that include any kind of geo-time? Like, for instance, if you can think of a parallel program that could use both an archival and an additional observing component?
I believe the answer is yes. I don't know if Neil is in the audience. Yes, he confirmed. So yes,
That's it.
includes
Okay.
that. Yeah.
Thank you. Great idea.
I agree, actually. And yeah, it'll be useful. Any other? Jeff?
Yes, you do. People online.
Do the content, trust me, everybody, please.
Yes, yes. So Jeff Valenti, he is the JWST mission scientist. He is in charge of the Data to Papers initiative. So if you have any issues about the pipeline that you want to highlight, if you want to, propose yourself to be part of the calibration workshop, please talk to Jeff. I think that would be very useful for everybody. Thank you, Jeff.
We have one quick one online. So John Debus has asked, is there any update on how scheduling of survey programs is proceeding?
Of how what?
The survey programs.
They are, yeah, the cycle 2 ones. Well, they are proceeding, like in terms of scheduling.
John, if you're online, do you want to unmic and chime in?
Yeah, I just was curious if there was a timeline for whether any survey programs have made it onto the schedule, or if there's any sense of timeline for when there will be a better estimate of survey completion rates.
I think we need to be a bit more into the cycle, but certainly we do need the survey programs to, when we have moments where there is not that much DSN coverage, we need survey programs to, have a lower data rate, and they will be utilized. So I think probably more into the cycle we can give actual numbers. Ori.
I think to follow up on that, the conversation is that at this point in cycle 2, there still are not any surveys programs that have been scheduled. So maybe there can be a comment on why that might have occurred. It's already 3 months in.
I think Massimo wants to comment on that.
Well, I don't know that I'll go to the why, but we see that there are places in the long-range plan where we are undersubscribed. We don't have enough geo programs to cover that 80% efficiency, and so we think we'll use the survey programs there. So we foresee using them. It's way too early to talk about completion rates and that kind of stuff.
There's another question online. Carl, do you want to ask it?
Yeah, hi, can you hear me?
Yeah. Sorry, we can't hear you now.
So right, okay, I was just asking what are the cycle 2 budgets results going to be released?
Sorry, which results exactly? I didn't hear that. Budget. The budget. The budget, the cycle 2 budget. Yeah, I don't know what that is.
So the committee is meeting this week, strategically on top of the conference, which makes it lovely for us. And so it will take some time after that, but maybe Neil can give it a tentative date.
Yeah, after the committee reviews them and sends them forward, there's a process to go through that involves approval from the project. So it's likely mid-November that the letters will be distributed to the community. And that's obviously later than usual, but we had to move everything late because of the late cycle. That's why cycle 3 is upon us so quickly. And next year, the letters will be going out before the start of the cycle.
Yeah, this year is nothing but, it's not a standard. Yes. Well, thank you, everyone.
We now have a round table with presentations from the instrument PIs, And we start with Mark Shariki, the NIRCam PI.
So good morning, everyone. It appears that the table got forgotten for a round table, but we'll speak anyhow. Okay, so I want to thank everyone who's used NIRCam because I've just been absolutely blown away by all of the great papers. And when the opportunity came to include me in this roundtable, one of the suggestions was, well, pick out 2 or 3 key results. And I said, no, I don't think I'll do that. But you'll see I've taken another tack because I didn't count up, but there's approaching at least 400 papers already out with NIRCam data. And I'm a speed reader, but not that good. And furthermore, 2/3 of the papers are on things that I know at the Astronomy 100 level, but not any deeper. So I'm not talking. I can't assess who's best in those areas. All right. So, needless to say, what I want to highlight is that we knew during commissioning that the results from our instruments were going to be absolutely spectacular. When we got this first image of what we called the evaluation star, which was, I don't know, HD 84800, and people figured out who we were going to look at early on. I've forgotten how that all went now, but this image was taken with the telescope aligned explicitly to NIRCam because NIRCam was used for all of the initial wavefront sensing. And so this image was one that was as perfect as it could ever get for NIRCam because NIRCam's good, but it does have a few built-in imperfections that are hard to avoid. And this particular image was taken with the mirror segments arranged to take out the wavefront error of NIRCam so that it was just as good as this telescope could possibly deliver. And of course, then we NIRCam reluctantly agreed that you had to tweak it for the other instruments a little bit because that was only fair. But this highlighted what I've come to view as the 3 reasons that NIRCam works so very well. This exquisite optical performance, and then when in the background of that star image, there's this beautiful collection of galaxies. And I thank Matt Lallo here, who is part of the wavefront sensing team, who went through that image and put them all together as a very nice mosaic. And this just highlights that NIRCam plus JWST equals absolutely exquisite sensitivity. When I think back to when I was a grad student and we could barely detect a nearby galaxy, this is like, whoa. And then the other thing that this highlights, and this image is at 3.5 microns, is that the addition of the longer wavelengths beyond what HST can do has yielded a lot of beautiful information on many things, not just galaxies and brown dwarfs, all kinds of sources. And so one thing that I want to highlight here is that this business of detecting galaxies in the backgrounds of images, if you look carefully at some of the first early release images, you'll find galaxies in the background. My colleagues who are doing coronography looking for exoplanets occasionally find these things in the background, and what is this? And I think back, I don't know how many of you remember the Twitter episode where there was the piece of chorizo alleged to be a JWST picture, and almost as soon as that appeared, people said, no, can't be a real JWST image because there are no galaxies in the background. Okay, so the image quality, of course, we've harped on that many times because we had promised to be diffraction limited. The actual requirement is written at 2.12 microns because that's where there's a NIRCam filter, narrowband filter you can test in. But the image quality is almost twice what we would have predicted. And that's just, how could we have, if I had known that we were going to have that level of image quality, I might have arrayed my pixels differently, maybe. I don't know, because we also still need field of view. And one of the kinds of things that one can point out are things like in this image on the right here, which is from a recently submitted paper by Adam Rees and his colleagues, this compares the purple or magenta colored filter labels indicate JWST and the other ones are HST. And this just sort of gives you an eyeball representation of how much better the spatial resolution is when you're looking at crowded places. And of course, what was interesting here was that Adam and his colleagues concluded that confusion is not the source of the Hubble tension, even though one does much better with JWST image-wise. And of course, the image quality comes in for many other projects. The one on the left is a little bit hard to see for sure, but the blue line is what a quasar plus presumably host galaxy looks like in this curve, and the red is a star, and you can see that even at Z of 6, we're now detecting host galaxies around bright objects like quasars. So another avenue for helping us ferret out black hole evolution versus host galaxy evolution. And of course, the middle image is showing that, although my colleagues used to say that, why are you bothering with coronography on JWST? Well, because the image quality is good enough and the sensitivity, particularly 3 to 5 microns, is just what you would like. Okay, and of course the sensitivity itself is at the best end of the predictions. That's partly a corollary of the exquisite image quality. And I just highlight here the arena where I have been most enchanted by this, of course, is deep surveys, looking for the most distant galaxies. And I'm pretty certain that before too many more months go by, we're finally going to crack that Z of 14 or 15 barrier and get even further out than the Z of 13 that we're at now. And then I think that people before launch tended to be somewhat Hubble-centric, and Spitzer did have some sensitivity at 3 to 5 microns. In fact, its channel 1, channel 2 filters are very similar to 2 of NIRCam's filters. But I don't think it had quite penetrated the consciousness of people about how useful this wavelength regime was going to be when you had the same kind of spatial resolution that you did at the shorter wavelengths. And this has impacted all kinds of things. The lower left there shows you many objects, pre-main sequence objects found in the Small Magellanic Cloud, not nearby, but in a whole nother low metallicity galaxy. And Mother Nature has been very kind to us because many sort of high redshift galaxies have very strong emission lines, which means that a mode on NIRCam that we had not really thought about exploiting the way we should have, and credit to Pascal Usch, who realized that the slitless grism would be great for searching for optical emission lines in moderate redshift galaxies, and that has become a fantastic factory for finding redshifts, and we'll learn a lot more from that. Thank you.
There is only time for one quick question. In that case, let's thank Marcia again for the talk and for building NIRCam. And Gillian Wright is the MIRI PI is the next speaker.
So I thought I would start by correcting Massimo. I'm not the Miri PI. I'm the PI for one half of Miri, because Miri was built in a very unique That better? Right. Let's start again. I am not the Miri PI. I'm the PI for one half of Miri, the European half, because Miri was built by a very unique collaboration in a 50-50 partnership between Europe and the USA. And that was what needed to be done in order to make this mid-infrared capability there. So I think I should also recognize George Reiki, who's sitting in the audience, who led the US part for as many years as I've been leading the European part. And Miri's kind of a dream come true in that adding the 5 to 28 micron wavelength range to JWST just adds enormously to what science we can do. And we only got one shot, so we packed absolutely everything in terms of coronagraphs, images, moderate resolution spectroscopy and low resolution spectroscopy, all packaged up into one instrument because we only had one shot. So I'm going to try and illustrate some of the things that Miri can do at all of its different wavelengths. And this is just some of my favorites that have made me go, wow, over the past year. So why is this not working? Pushed it the wrong way. So galaxies, these are not the pretty images of galaxies, but by adding mid-infrared wavelengths, that opens up the possibility of looking at galaxies in the near infrared, so looking at the underlying structures in the old stellar populations. And we are seeing, maybe it's not a surprise, but it's nice to see it, the galaxies with the smooth structures at the longer wavelengths where you're seeing the older populations and you're not so dominated by regions of star formation in the galaxies. And this also extends out now to spectroscopy and to the examples of a quasar where the FITS, this quasar is at a redshift of 7, but it looks like a quasar in our nearby universe in terms of the line emission and the line ratios and the excitation. And I think that's a bit amazing, really. So, and this is a perfect example. So the first one was an example of sensitivity matters. It's the amazing sensitivity that allows us to look at those old stellar populations in moderate redshift galaxies. This is a perfect example of spatial resolution matters and what you can do when you have spatial resolution in the mid-infrared. So it wasn't unknown that there was some kind of a ring of dust around this pair of stars and that dust was being forming. What was news was to be able to see 17 rings and to make such a beautiful model of how those rings are created that fits the data. And it's a lovely picture. So moving on from stars dying to star formation and exoplanets, Miri also has coronagraphs, and they are also finding little redshift 1 black background galaxies. This is the first image of a planetary system as well as images of the planets. We can image systems, and in this case, in HR 8799, it was expected that there would be an inner disk. It's the first time it's actually been resolved and seen. We can make temperature measurements. That's the fantastic stability of JWST photometry, so that you can measure tiny differences in signal when the planet is going behind the star. And then with that, it's possible to start getting at the atmospheres or the non-atmospheres of rocky exoplanets. So this is the work that's been done on TRAPPIST, and I think there's a lot more data on TRAPPIST to come from JWST. So it's just a taster of how not only JWST, but having the mid-infrared capability is changing how we understand exoplanets. We put in, well, medium resolution spectroscopy, chemistry. We can do chemistry. So the image on the left goes from a young protostar to a very low mass brown dwarf. And you can see the rich chemistry. So all the wiggles in these spectra, they're real features. They're not artifacts of the spectroscopy. And it's just an incredible amount of detail now that we can get to in the chemistry of what's happening in young stars, star formation regions, and where planets are forming. So I think, you know, a perfect example of this is the finding of water. You can see how beautifully the water model matches the MIRI data with all these real features. But this is in the terrestrial planet-forming region of a young protostellar protoplanetary disk. So again, the chemistry is really exciting. Everything we're looking at, there's something new. And I saved the best one for last. I think this is the MIRI poster child, really. It's the Fomalhaut debris disk, and the way that first of all, it's a stunning image, but all of this structure in the inner warm dust and the kind of so this is a debris disk, so it's a mature system. It's not forming planets now, but what we're seeing in the structure of the rings is almost certainly the hollowed out features of the dust. It's far more, these debris disks are in some ways analogues too for the Kuiper belt and the asteroid belts, but this is a far more complex system. The one ring was known from the ALMA, so this is the original 25 micron image and also the 15 micron image compared with ALMA and Hubble data. So that was the end. I wanted to finish with a big thank you to the MIRI team. Many of the people that you can see in the old pictures all the way back to 2010 and the people in the recent picture taken last year during commissioning, many of those people stayed with MIRI the whole way, and it's people that made MIRI happen. So from me, a big thank you to everybody.
Any question for one of the two copy eyes of MIRI? Don't see any, so let's thank Gillian again. Is he remote as well? So then,
There's also project scientists that are very important. Okay, can you hear me? Okay, first, thanks for the opportunity to talk to you about this, what an incredible year. NIRISS is not the same game as NIRCam or NIRSPEC or MIRI in terms of scientific productivity, but it's been quite a lot. And so what I'm going to do is give you highlights of what's going on in the project I've been involved. So that background capture what I'm going to talk about, high reach of galaxies, extragalactic science, and sorry, exoplanet science. So just a few words about this big program we have within NIRISS called Canucks, which is about a survey of galaxy clusters to study galaxy evolutions, and one very important component of that program is grism spectroscopy. It's a comprehensive program that uses NIRCam, NIRSPEC, and WIFIS. So these are the beautiful clusters that we have. All data has now been acquired already. So this is a first result that came out recently, which is a large catalog of redshifts done with NIRISS. And interestingly, you see some of these excess at some various redshift. This particular galaxy here, where we can do a dust attenuation map using the wide field spectroscopy capability of NIRISS. And this one here, which is very, very interesting, this that's coming up, the cosmic question mark. which is obviously a lens galaxy. And in fact, the preliminary analysis that is coming very soon is a story about actually two galaxies, one blue face-on galaxies and a face-on, edge-on red galaxy. So WIFIS give us a detailed map of with H-alpha on this. Okay, so move on to the transmission spectroscopy. So that was the ERO on the WSP 96. There was quite a few papers published on this, but there was also one target as part of the ERO package, which was at 18b, and it was a paper published very soon after by Fu et al. That published the data, but a more recent analysis, and let me echo this work by Marie-Lou Fournier-Tondo, that has a poster here, which is the first time that one does a joint analysis of the stellar activity. There's a clear spot crossing event there, but there's also unocculted faculty. And the result of that is actually quite different from the analysis where you would just do a normal, naive correction from the stellar activity. One also from the WSP 18 phase curve, a complete phase curve with NIRIS, that gave us gory details about the temperature profile, a map, metallicity, and one plot that caught my eye, which we had a preview at commissioning, is the noise floor. So when you beat that, you go down with time, there's now evidence that noise floor is less than 5 ppm. It's probably less than that. So there's probably no noise floors with JWST, but you have to worry about other things like systematic effect. TRAPPIST-1, this is in green the data that our team have access to. Our GTO program is focused on F and D, but Olivier Lim, my graduate student at UDM, is actually leading a community program to do reconnaissance spectroscopy with NIRIS and NIRSpec on B, C, G, and H. So I'm going to talk about some of these results, first on B and with NIRIS, and G on NIRSpec. So B, so the paper has just been accepted as last Friday in the AppGL. So this is the first transmission spectrum of TRAPPIST-1. Please don't take pictures. And the main story here is one of stellar activity again. So the two visits, we have two visits, and they're quite different. And you see in orange here is actually the spectrum is not flat, but those are due to stellar unocculted spot, the so-called transit light source effect. And one thing that was really surprised me is that one good surprise of commissioning is that there's very good blue response in NIRIS, and you can detect H-alpha. In fact, there's a feature on the continuum, but we can really detect H-alpha, and you look on the second visits, you may think that there's something looks like a spot crossing event, but it turns out it's not. With H-alpha, it's a mini flare. So NIRIS turns out to be a very powerful capability to map the stellar activity in these systems. So yeah, this is the thing that we have to worry about. The transit light source effect, that if you have unocculted spot or faculty, this will bias your spectrum, even if your planet is airless. And this is a cartoon simulation here showing what spectrum you will get, and you really need to take that to model for this now, and that's what the nearest observation is actually showing. Now for G, that one is actually with NIRSpec. That one is very surprising. We had an incredibly flat spectrum down to 30, 50 ppms. And in fact, this one, the transit light source effect appears to be much less than about an order of magnitude. So maybe it tells us something about the latitudinal distributions of spot, because G has a higher impact parameter, 0.4 instead of nearly 0 for B. But this is a really exciting result. And for that specific paper, we can exclude a whole family of secondary atmosphere with only one visit. So it calls for more observations here. So this is under review at Nature. So one big story about TRAPPIST-1 is flares. There's lots of flares coming out, typically 1 out of 2 transits. There will be a talk tomorrow by Ward Howard on this. And so this is the case, an example here in NIRSpec where we saw a big flare. So unlike NIRSpec cannot resolve, NIRSpec Prism cannot resolve the H-alpha, but you can do it differentially. You take a portion of the time series that is relatively quiet, and then you subtract it, and you can actually detect H-alpha. And so, yeah, this is flares is a big deal. You'll see tomorrow there's good sign, the good encouraging sign that one can correct for it, but whether we can correct it to the several tens of ppms that we need to do this thing is yet to be demonstrated. So there's a lot of observation that's been acquired so far in a year. So what is the next step? So there's a paper under review right now that I'm collating with Julien DeWitt that basically says three things. First, we need more observation with MIRI. MIRI has been extremely powerful through eclipse mapping to probe the inner planet. But for the other one, there's no other way. We have to do transmission spectroscopy, and we need to characterize the solar activity. So what we propose is a full rotation with NIRISS-SOS, and then a multi-cycle deep observations with NIRSpec using a multi-transit approach, because this is a much more efficient way of doing this. So that's it. Thank you.
Any question in the room for René? A lot of cell phones taking pictures. They shouldn't.
That one is fine.
Oh, that's one is. I don't see any takers, so thank you, René. The next talk is online. Roberto Maiolino will be speaking on behalf of the NIRSpec team.
Just a second. Right. Can you see the screen? Hello?
We're still working on the presentation, and I'll try to use the force to communicate 2 minutes.
Can you see the screen? Hello?
Can you hear me?
Yes.
Okay. We're still trying to set it up.
You see it online, but
Can you hear me?
Yes, we can.
Then
We are not seeing the presentation on our screen.
we worked a few minutes ago. Right. That's me. Can you see it now?
We can see and hear you fine online.
But can you see the presentation? I'm sure it claims it's being shared.
Yes. I can't see it in the room, but online we can see it.
Okay, we are now ready.
Not your problem.
So we are ready for the presentation.
Can you see it now? Yeah.
Your go for the presentation.
I'm sharing. Can you see the screen?
Affirmative.
Okay. Okay, thanks. Sorry for the glitch. So, hello everyone. Sorry for not being there in person. So I was asked to illustrate a few, 2-3 of the NIRSpec's highlights, and of course, as for the other instrument, it's really a difficult choice because there has been so many fantastic results from NIRSpec during the past year. Before I start, let me acknowledge that NIRSpec was developed by Airbus Defence and Space for ESA, with also a contribution from Goddard for the detectors and microshutter array. So before launch, I was often showing this slide where I was making the point that with JWST, the leap in sensitivity is huge, especially with spectroscopy, up to 3 orders of magnitude in some bands. And this has happened very rarely in the history of astronomy, and more broadly in the history of science. And I was making the point that essentially this is equivalent to instantaneously upgrading the Galileo's telescope to modern large telescopes. So you can think about 400 years of discoveries compressed in the time frame potentially of the JWST. So after 1 year, maybe it's time to see whether JWST and in particular NISPEC is meeting these expectations. Now, NISPEC has contributed to all areas of astronomy, and for the solar system, I have picked this result, which is really exciting about the discovery of water ice around the comet in the main belt, which wasn't expected there. And so it's a very fascinating discovery. And as many discoveries, it comes also with new puzzles, in particular the non-detection of carbon monoxide, which is, there are some possible explanations, but still it's puzzling because it was expected to come along with the water ice. And within the context of icy water in the solar system, I've also been fascinated by this detection and mapping of the icy water plumes erupting from the underground oceans in Enceladus. That is also very important implications. Of course, for NISPEC, there were great expectations for exoplanets, and the first results have not disappointed. This is one of the results from the ERS team with this fantastic transmission spectrum where you essentially can detect with fine detail all these molecules in the atmosphere of these giant exoplanets. And this really mind-blowing that you can get this kind of details of the composition of the atmosphere of a planet outside our solar system. So, and even exciting, as René has also pointed out, is that now we are actually capable of characterizing the atmosphere of Earth-sized exoplanets. And this, in this case, the detection is featureless, so it's a spectrum, and these sort of exclude Earth-like atmosphere, so you can constrain other kind of atmospheres. But the point is that we are capable now, with just 2 transits in this case, of detecting and characterizing Earth-like exoplanets. So this is really fascinating, and I'm sure that more results will come on this in this regard in the coming year. Now, jumping from exoplanets to the most distant galaxies, it's been an exciting year for essentially confirming finally the redshifts of many of the most distant galaxies from beyond redshift 9, 10, and 13. However, it's not just the redshift confirmation that is exciting. The fact is that many of these galaxies have show nebula lines with fantastic signal to noise. And for instance, we are capable of detecting even the auroral line, particularly secretary of oxygen 3. I must say that before launch, at whole conference, people were saying, okay, we may be able to detect these auroral lines up to redshift of 3, but clearly redshift 6 reionization is completely out of reach for JWST. And now here we are, where essentially this auroral line is detected beyond redshift 10, and this allows to determine the electron temperature, which in turn allows us to measure directly the metallicity. So it's really fantastic that we can make detailed atomic physics just 400 years after Big Bang. Okay, and the other interesting finding is that in many of these galaxies we detect now Lyman alpha, which was also in faint system, which was unexpected this high redshift. So there are various possible scenarios being proposed, so large bubbles created by overdensities, AGN contribution, and these are keeping many of us busy these days. With this detail, I mean, high signal spectra, we can now characterize the metal enrichment of these systems. And we do see a mild evolution of the metallicity, but actually relatively mild, considering that we are going expanding most of the lifespan of the universe from 400 years after the Big Bang all the way to the local universe. However, as is illustrated by this fantastic spectrum by the team of Van Zel et al., we are actually now approaching also extremely metamorph systems. In this case, is a galaxy with extremely, low mass, which has metallicity which is about 10 times lower than solar. So we are actually indeed approaching the extremely metal poor scenario, possibly towards population tree. And indeed, there are some potential signatures of population tree that probably will be discussed later this week. The other fantastic result from NIRSPEC has been the detection of AGNs and high redshift and the characterization of the associated black holes. And here taking this iconic spectrum from Hubler et al. Because this is an AGN essentially close to the epoch of reionization, and as it's not particularly luminous, it's far less luminous than a quasar. And despite that, the signal to noise of the spectrum is mind-blowing. I mean, to illustrate, to show the noise, she had to plot the spectrum with a logarithmic scale, okay? And at that point, you start seeing some wiggles at the bottom. So some of these lines has signal to noise of thousands. So, and we are again close to the epoch of reionization. Now, it's difficult to obtain this kind of spectrum even in actually local AGN, so it's really impressive. The important thing here are this detection of these broad lines, which allow us to measure the black hole mass associated with the AGN. And these black hole masses are now much smaller, of the order of a few million solar masses, than what measured in the previous surveys before JWST on quasars. And as mentioned earlier on today, these seems to be actually overmassive relative to the stellar mass of the host galaxies, relative to the solar relation. Local relation. And now how overmassive is difficult to, determine exactly, because determining the stellar masses at such a high redshift, and especially if you have an AGN, is extremely difficult and with a lot of uncertainties. But I think is beyond doubt that most of them are actually overmassive. And this has implications for the understanding the seeding of these early black holes and their accretion properties. Connected to this has been also fantastic, the discovery of so many passive and quiescent or recently quenched galaxies already in place in the first 2 billion years of the universe, which essentially is telling us that everything in the universe happens much faster and more dramatically than we thought. It is star formation, not only star formation has happened much more faster, but also its quenching actually happened very quickly. And this may have been associated with the AGN quenching feedback, but also burstiness and other phenomena. And this is essentially, there are a lot of new results that have been published these days. And I'm sorry that I couldn't illustrate many more highlights that have been published and results in the past years. My selection has been, how to say, nearly random, because all of these results are really fantastic. I wish I had more time to illustrate all of them, but of course, there is a limited time. So thank you.
Okay, I don't see any hand. So thank you, Roberto. And before closing this session, I'd like to thank again all presenters, and I would especially like to thank all the teams who build fantastic instruments for JWST.
Just a couple of quick practical announcements before you head off to coffee for those here at the Institute. So we've had a few questions about all the posters on Slack in particular for the participants on Blue Jeans. So if you go into the Slack channels and browse for the different channels, there are separate channels for each of the poster topics, and the digital posters will be in there for the whole of the week and for a few weeks thereafter. Equally, there are different sessions in Slack for each of the different science sessions, so I encourage you to go and have a look at those as well if there are questions. For those in the room at the Institute, the password for the local guest Wi-Fi is on the wall on these two posters if you need that. And otherwise, I think that's us for coffee. Is there anything else we should mention?
I'd like to reconvene at 11 o'clock to get back on schedule. Thank you.